Okay, guys, welcome back. I have a collection of announcements about forms. So remember, the time for filling the form about the boat trip is about to finish. So if anyone that wants to go in the boat trip has not announced this in the Google form, please do it immediately before Glaucia starts her talk, because when he's talking, is not the time to fill any form. Irrespectively, I'll talk about other two forms. One that most of you probably already received in the WhatsApp group, that is thanks to Carolina and her team. And she's organizing a way of I have something to dress in some years in the future. Because if you could not recognize, I'm using one t-shirt from the second edition of Paraty, and I need something to dress about the 8th edition of Paraty. And she has organized it to you to manifest, okay, I want 5 t-shirts. And you go there and say something like this. Remember, Father's Day is approaching, it's a very nice gift in itself, as well as a Shasta that we still have here. And okay, so this is the second form. And the third form was already announced before, that we have the round table this afternoon, well, almost this evening, and we are collecting questions to make the roundtable more interesting, to not make you shy, and etc. I think the form is not available yet, but it will probably be available soon. But again, you should not bother about it before lunch. But when Glaucia finishes, you probably have not to bother anymore with the form of the boat trip. If you have filled, great. If you did not fill, your problem or your decision not to go. But the other two are important forms because Carol needs, and this you don't need. You need as soon as possible, but without a clear shortcut. And of course, the roundtable is this afternoon, so it would make no sense for you to fill it after the roundtable. And now I pass the word to Barbara, please.
Hi everyone, good morning. I am very happy to announce the next course. Now Gláucia Murta is going to talk about some proofs in cryptography, and I'm really happy because I've known her since we were undergrad students. We've been in your place together a few years ago, and she did her PhD with Marcelo, and so did I. So we shared our sufferings during her PhD, and then she spent some time during her PhD. She spent some time in Poland, in Gdańsk. Then she spent some time in Delft, and now she's a principal investigator in Düsseldorf in Dagmar Bru's group. And Glaucia, I'm really happy to have you here. Thank you for accepting our invitation, and have fun.
Mm-hmm. And thanks a lot, but this is very hard. Okay. Better. Okay, good. Yes. Yes, so it's a really big pleasure for me to be here, so I thank the organizers for this invitation. Maybe going back to this non-Markovianity just to mention. So the first 2011 was actually my first conference in quantum information, so I was in Paraty as a master student, and then I also came again at the following years, now as a PhD student. And I was organizer of the Casaloma, so this should add to my CV as well. Right. Okay, then unfortunately I have a break of Paraty for some time, but I'm very happy to be back here and to have this opportunity to teach day school. And yeah, I hope to keep coming back more often. Yeah, so what I want to talk about in this course is, let's say, maybe much simpler simpler setups than what has been discussed in Richard's and Fernando's course, because they are interested like in doing complex quantum computations or evaluating systems that have many qubits and so on. But I actually want to talk about a task that we can do just in the simplest case already, where we have only just qubits or maybe 2 qubits, and we can get something fundamentally very interesting, which is secure communication. And my goal in this course is to really go through the steps that are part of really making this protocol properly formalized so that we can achieve secure communication. Okay, so basically the task that I'll be talking about in general is actually a classical task. So the idea, we have Alice and Bob, and the goal is that they want to establish a secret key. So this is basically a string of bits. Here we have L bits, and they should be completely random. Well, and the goal at the end is that, well, at the end Alice should have a key that is equal to Bob's key, and Eve doesn't know the key. So I'm experiencing in writing in this device, so if you don't understand my handwriting, please shut out and try to do. So in general, like this, the task is we want to establish a secret key by using 2 resources. So here we are going to, Alice and Bob, they have access to a classical authenticated public channel. And this means that they will just communicate publicly, but here it's authenticated to say that when Alice is saying something, Bob is sure that it's Alice. It's not Eve impersonating Alice and trying to say something. And another resource that they are going to have is that they have this quantum channel, which here could be insecure. And this is pictured here because we have an eavesdropper, and you see that the red circle is both like covering the classical channel and the quantum channel. So the task that we want to address is like, okay, how can we use this insecure quantum channel? So use quantum mechanics to, at the end, establish this secret key, which should be equal for Alice and Bob and unknown to the eavesdropper and anyone else. So my goal of today is to really go through all the steps of the VIII protocol, so a specific protocol for quantum key distribution that I hope, and this will be very important because in the remaining 2 lectures I will be really going into the details of how we prove security of this protocol. So for that it's important that really the protocol is clear to everyone. So in this picture here, so I came from this standard generic protocol to now more like which protocol are we going to be talking about, and this is a schematic representation of the VIII protocol, and things will be more clear in detail what do I mean by these different errors if you are not familiar with it. Maybe I could ask how many of you have heard of the VIII protocol before. I hope maybe everyone. Not everyone, but almost. And maybe have heard more in details of all the steps and security proofs. Okay, some as well, but not so many. Okay, then very good. Okay, so the main idea, which is actually depicted by this arrow here, is that, so how are we going to make use of quantum mechanics? So the goal is that Alice wants to send a bit for Bob, so that this will be their key, and the idea is that they are going to encode the classical bit using non-orthogonal states. Orthogonal states. And this is actually, we are making use of explicitly this point. So Richard was telling in his course today that in quantum mechanics we have a problem that when we have a system and we make a measurement, we lose the system. It's a one-shot thing. So actually, to know which state we have, we would have to repeat it several times. For cryptography, we are going to make use exactly of this fact that when I have a system, I make the measurement, I cannot know exactly which state I had before because I destroyed it. And this will be the crucial point that actually will forbid the eavesdropper to actually know which state were there. So we can go about what do I mean by this encoding non-orthogonal states. And basically the idea of the BB84 protocol is that I have Alice. And if she would like to send to Bob, so here I'm saying the bit A is equal to 0, she has two options. She can either send it by preparing the quantum state 0 or by preparing the quantum state plus. And if the bit is 1 that she wants to send, she could prepare the state 1 or prepare the state minus. Okay. And then she sends it over the insecure quantum channel, and then Bob, who is on the other side, what he's going to do, he's going to measure this bit. Okay? And he has two possible options. He can either measure in the Z basis, or he can measure in the X basis. And maybe here I can just quickly go back to my picture where here I'm representing states prepared in the Z basis, and here would be states prepared in the X basis. While in particular, in this case, my qubit could be the polarization of the photon, for example. And the same when Bob is measuring, he could either measure in the Z basis, which is on the left side, or in the X basis, which is on the right side. So he's just checking the polarization of the photon. Okay, and then Bob records the outcome. It's going to be the bit B. So what happened when Alice prepares the qubit in the Z basis and Bob measuring the same basis as Alice? What is the relation between A and B here? Right, so if Alice prepared the Z basis, she prepared the state 0, Bob measures the Z base, he's going to get the state 0, and he's going to say, okay, I know that the bit was 0. So they are exactly the same. So actually this will be the crucial idea, and this string of bits that Alice prepared and Bob measure, they will going to form the key. So they will form the key. But what happens when Alice prepares on the Z basis and Bob measures on a different basis, on the X basis? Maybe what's the probability that A is equal to B in this case? Half, no? So they are completely uncorrelated. So I have that A is equal to B or A is different than B. Exactly equal to half. So these rounds are not very useful, so they will not form our key. Okay, but so yeah. So what about Eve? No. So what if Eve tries to find out about A? Okay, so Alice prepared the state, and then Eve is going to do something there. So she could, for example, measure the state. So suppose Alice prepared the 0 state, and then Eve was there, and then she measured in the Z basis. That is fine. She's going to get 0. She can prepare it and send to Bob. Bob measuring the Z basis, he gets 0. They are happy because A is equal to B. But if she measured in the X basis, for example, then she completely disturbed the system. She could have get plus or minus. Then she prepares it, sent to Bob. Bob measures in the Z basis. He might not get A equals to B anymore. So maybe A could be different than B for the same basis. So the crucial point of QKD, if Eve tries to interfere with the channel, she's going to disturb the channel. So the idea here is that Eve can be detected. So basically, and this cannot happen classically. Classically, if Alice was sending a bit to Bob, Eve could simply copy these bits, okay, it's 0 or 1, she's observing it, she's copying it, so she has information, Bob has the same information. But here in QKD, whenever Eve tries to get any information about what is the value of A, she might disturb the value that Bob is getting. So basically QKD is allowing us to detect that we have an eavesdropper. Okay, I mean that's good because whenever I have an Eve, I could just say, okay, then let's abort the protocol and we don't use this key whenever we have an eavesdropper. But the problem is that sometimes in an experiment, I don't really have an eavesdropper, but I have a very noisy channel. So there's no eavesdropper, but somehow A is not equal to B because maybe there was a dephasing or depolarization that happened in my channel. So if we use only this strategy that whenever I detect the eavesdropper, I abort the protocol, I would never generate a key. So that's the crucial part of these security proofs, is to say, okay, I have some noise, I don't have A equals to B. This noise could be a real noise from my implementation, or it could be the eavesdropper. So yeah, here in the very malicious scenario, whenever I see a noise, I can say, okay, this is information that the eavesdropper has. So how can we establish a secret key even in the presence of noise, no? So we want to make let's say, make a quantitative statement about the key rate. We want to have a realistic protocol such that I have noise in my lab and I can still establish a secret key. Yeah, so that's our goal. Good. And maybe I would just like to comment that, I mean, at the moment, QKD is one of the most developed quantum protocol that we have like several different implementations with quite high noise tolerance, quite high rates. So it's really very good, but how is it possible? So that's what we are going to learn here in this course. Okay, so I mean that was a big picture of the VIII protocol. Is there any question at the moment already? If not, then I now would like to really go into the details of the VIII protocol, and I hope you stay with me for that. So we are going to see what are the steps, no? Because at the moment I just said, okay, Alice send the state to Bob, Bob measure, they record the strings A and B. So what are they going to do with these bits that they recorded A and B in order to finally get this secret key? So I'm going to prepare to start explaining a version of the VIII that is called prepare and measure. And at the moment, let's just take it as a name, but afterwards it will be clear what is the meaning of this prepare and measure name for the protocol. Okay? So the first step of the protocol is the distribution and measurement. Okay, so here basically I want to describe all these first parts that we discussed so far, but more in a protocol language. So what is going to happen? Alice on her side, she's going to choose two random numbers. So she picks X and A that are either 0 or 1, and then she prepares the state. So as more or less I explained before, the X equals 0 will represent the Z base, so she's going to prepare a state in the Z base. So either if A is equal to 0, she prepares the state 0, or if A is equal to 1, she prepares the state 1. And the same thing if now she chooses X equal to 1, she's going to do a preparation in the X base. So A is equal to 0, then she prepares the state plus, or A equals to 1, she prepares the state minus. Then Alice's Alice sends the state to Bob, so she distributes the state. Bob, on his side, when he receives the state, he's going to choose another bit. So Bob picks Y, which also belongs to, so it's a random number, either 0 or 1, and then he measures depending on the Y. So if Y is equal to 0, this corresponds to a Z basis measurement, and Y is equal to 1, he makes an X basis measurement. And finally, Bob records the outcome B. Okay, so far it's everything, this initial part that we explained. So now comes a new step for the protocol. So, okay, they are finished, so they repeat. Actually, they should do it n times. Oops. So they repeat several times. Alice picks this number. She encodes the bit A using either the basis Z or the basis X. She sends it to Bob. Bob makes a measurement either in the Z basis or in the X basis, and he records the outcome Y. So at the end of this step, let's say Alice has a string, and here I will represent it like that. So this is A1, A2 until AN. So this is a string of n bits, and Bob has a string of n bits. Okay, now in this step 2, it's called sifting. So basically the idea here, they want to check what are the rounds that are useful and which rounds are not useful. So for that, they are going to publicly announce X and Y. So they are going to announce which bases they use for preparation and which bases they use, which bases Bob used for the measurement. Okay. And what we discussed before, if X is different than Y, this means that either Alice prepared in Z basis and Bob measured in X, or Alice prepared in X and Bob measured in Z. And you told me that the bits A and B are completely random, so they are equal or different with probability half. So this is very bad round, so they are going to discard these rounds. So at the end here, so before they had this very big string of n bits, now they have a smaller string of like, let's say smaller n now. Okay, now in the third step, they want to check if the eavesdropper was really there or not. So if there was no eavesdropper or no noise in the channel, so they basically have completely equal strings. So the string of Alice is equal to the string of Bob. But actually in practice, that's not going to be the case. So this third step is called parameter estimation. And now it's the only part that is a bit more, well, not the only part, but a bit more specific for the VIII protocol. What are the parameters that they are going to estimate? Okay, so for that, they use some of the rounds. To estimate let me write first. These two parameters. Okay, and by using some of the rounds, it means that they need to communicate with each other. So they will tell out loud, remember they had a public channel, hey, in this round my outcome A was 0, and Bob says, oh, my outcome A was also 0. Or my outcome A was 0 and my outcome B was 1. So there was a bit flip. So basically they want to estimate these probabilities. So they will use some of the rounds, and these for such estimations, this type of techniques that Richard discussed of Hopkins inequality, or in his case more general things, because we don't want to assume that we have the same IID realization, but okay, details that will come later. But the idea is they will have some statistics, and then they can look and estimate about these two parameters, okay? If there was no eavesdropper or no noise, Qx and Qz should be 0. But if there is some noise in there, then they are going to be aware. So they are basically detecting the eavesdropper in this step and how much the eavesdropper might know about this string. So these things are called Q pairs, which stands for quantum bit error rate. Okay, now finally they estimated how much their strings are not differ from each other. Basically now they want to correct so that they have the same string. So this step is called information reconciliation. Or sometimes you hear people just saying error correction. And the idea here that Alice will send information to Bob so that Bob can correct more properly. So now, remember, they started with capital N, and then they lost some bits on the shifting. So part of the key was lost. Now part of the key was used for parameter estimation. So they have an even smaller string. Let's call it M. So basically, the idea here is Bob had a string of M bits, and then he will use this information reconciliation to estimate another string, B tilde, which hopefully is equal to the string of Alice. So if this error correction procedure, this information reconciliation worked fine, then they will get the same string. And here it's what it can correct. Basically this step, the amount of information here is based on a classical error correcting code. Error correcting code. Again, later we will discuss a bit more in details for this step, but for the moment, Alice sends some information to Bob, and Bob can correct for this string. So good. So now they, if I go back to my drawing, basically now they satisfied the first one, that they have two strings of bits that are random and they are equal. But we also would like that Eve doesn't know anything about this string. And again, because we have some Q-bars, we know that Eve knows something about this string. And because all the communication that Alice and Bob do in this step 4, Eve is listening to it. So this is information that Eve is getting. So, and again, here we are paranoid. We say every information is very precious and gives relevant information to Eve. Even though Eve might not be able to listen to it, doesn't matter. We account for it. So basically we need the final step, because now Alice and Bob have a perfectly correlated string, but it's also correlated to the eavesdropper. So now we would like to remove this correlation with the eavesdropper. So this is called private simplification. And basically the idea here, so Alice and Bob, now they have a string of M bits. They are going to do a procedure that will bring them to a smaller string of L bits. That was the letter I was using before. So L is smaller than M, and the same for Bob. Actually Bob tilde, because he's using his corrected string. So it's shorter, but let's say KA and KB are secret. So that means that they are unknown to Eve. So And that's the end of the protocol. So now they have the secret key, and we are going to discuss the steps more in detail, but I want to be clear that, okay, first phase, they just do this distribution and measurements, and then they account for the fact that whenever they measure different bases, it's completely useless information, so let's throw it away. Then they estimate, okay, Eve might know something about my string of bits. Eve knows she spoiled the string of bits, so first we need to correct, and now we need to remove all the information that the eavesdrop knows about it. Okay. So if this is possible, then at the end, Alice and Bob, they will have a same string of bits, which is uncorrelated to the eavesdropper, even though we were in the presence of noise that generated these Q bears. Okay, so before I make some remarks about the protocol, is there any question about the protocol, or is it? Yeah.
Step 3. Okay, in step 3, how do they choose which rounds they're going to use to estimate those? Do they need to talk prior to say, in round 1, 3, and 5 we're going to say...
Yeah, okay, so which ones they are using for parameter estimation, right? That's your question.
Yeah, they need before to say which round they're going to use, or...
So they could say before, but this has to be sampled randomly. Because the statement you want to make is that I observe this frequency in this smaller string, and I want to infer that my big string has the same Q bar. So you are using this type of concentration bounds here to properly estimate it. Although you are, because I'm not interested in knowing the Q bar of the rounds that I throw away, I would actually like to know the Q bars that I have on the leftover string, these ones here. So that's why they have to be chosen randomly. If they are deterministic before, Eve could know in advance. And again, the idea of crypto is all the specifications of the protocol, they are public. So as long as you need to have secret information, it's not a very robust protocol.
So the whole protocol works if Alice and Bob met before in person?
Might do it?
So they met in person before?
Okay, sorry. They could, for example, Alice could have a random number generator on her side, and once, if the measurements are already performed, she could say it out loud, Bob, now we pick round 1. So it's important that this is picked after, or uncorrelated with the distribution of the state.
So it's okay if you know before. Okay.
If she knows after she distributed the state, she cannot tailor distributed, or after she acted on the channel. So Bob has to have completed his measurement, yeah.
Okay, thank you.
I have one question. These steps 4 and 5, they are done after the quantum thing is over, right?
Yeah.
So is there any specific error correction and privacy amplification for quantum generated keys, or is this the same that is used in classical protocols as well?
So here is the same that is used in classical protocols. So it's a quantum error correction code, and I will talk more in details, and this is a hashing function. In fact, you can see that actually these two steps corresponds to an error correcting code. This is not very explored, but one of the, I forgot to mention, so the VIII protocol was proposed in '84, but the first security proofs are from 2005 and 2006, and one of them is based on distillation. So basically you are doing quantum error correction, so there is a CSS code that corrects for bit flips and phase, and basically this information reconciliation is correcting for bit flips, and the private simplification is correcting for phase flip. So in a sense, they two correspond to one error correcting code. I'm not sure if I can say that this is general for any protocol. For the VIII protocol, one can see that. But in general, this would be just classical steps independently. And you could choose other, you could choose protocols where here I said only Alice sends information to Bob, but they could have more iterations, and this would be another classical error correcting code. So maybe I wanted to make some remarks, and one of them Barbara already said, is that, so the protocol has 5 steps, well, except that the first step is repeated many times, but the quantum part ends here at the end of step 1. So everything else that I'm doing is just classical post-processing. So, and that's why QKD is a simple protocol, because we don't need memory, we don't need to do a global operation. We are simply, Alice sends some qubit state to Bob, Bob measures, and then the quantum part is over. Afterwards, it's their problem to do all this very complicated classical post-processing of the data. So maybe to write it explicitly, the remark 1 that one part ends at step 1. So basically, this protocol is more simple to actually implement than to prove the security in fact. Another remark that I wanted to make was related to the question about how they choose the rounds that will be used for key generation or for parameter estimation. In fact, we can, so here I said that they choose randomly x and y between 0 and 1, so the bases that they choose to prepare. We can make this protocol much more efficient. So, more efficient protocol. Let me write and then I speak. So, we can actually bias how Alice chooses the bases. So she could choose the x bases much more often than the y bases. Oh, sorry, then the z bases, the other way around. So let's say on their side, they choose so x equals 1 and y equals 1 corresponds to preparing and measuring the x bases, and here preparing and measuring the z bases, such that we don't have to throw away half of the rounds in the sifting. So here in the sifting, whenever they have different bases, they throw away the rounds. And instead we can say, okay, actually they tailor this probability, so they have to throw away the rounds with probability gamma squared, gamma times 1 minus gamma, anyways. With okay, I don't think this number true, but homework, with a smaller probability, they have to throw away the rounds. So in this case, we can actually do something that whenever I choose the z basis, which is chosen more often, this will be my key generation. So I would use it for the key. So we call it the key generation basis. And then whenever I have the x basis, I use it to do the parameter estimation. I don't use it for the key. So this is a test basis. So, I mean, also from the theoretical perspective, it is easier to make the analysis of this protocol, but in some implementations, the choice of bases is passive, so they don't have control. So then for them, it's more advantageous to use the half-half bases. But if you do, then it's better to tailor this basis so you don't throw away many of the rounds. Good. Questions? The passive choice of bases.
It's so well defined how they avoid E to simply always try 0.
Okay, Eve can always try the 0 basis, but then there are 1 rounds, and in these 1 rounds, Eve will be detected. So, yeah. So, I mean, asymptotically, we are going to make this 1 round goes to 0, but they need to exist to detect E. Okay, so now I would like to discuss, so we have the protocol, I explained all the steps, but what are the assumptions that are present in this description of the protocol? So what are we assuming when I say all of these steps that happen here for my protocol? So any ideas? yes. Okay, I will add this one. Indeed, so someone said quantum mechanics works, so I'm assuming quantum mechanics. Good.
Dimension.
Larger dimension. Yes. Okay, I will write dimension later, but it's even stronger than dimension.
Devices are reliable.
Devices are reliable? Which devices?
Like the measurement ones, the sources of.
Okay, the sources, yes. Okay, so then it's connected to Nigel's answer. So he said the measurement devices and the source. So basically, Nigel said dimension 2, because, okay, here I'm saying that I'm preparing a qubit, not something else. Yeah.
Perfect single photon generators.
Ooh, yeah. So, well, if it's a photon, no? But, so exactly. So all these comments related to more.
A good randomness choice for
Yes, as well, no? So here Alice speaks the numbers. If Eve knows how Alice is speaking the number, also connected to her question from before, Eve can just tailor the rounds. Okay, I will collect all and then I write them afterwards. What else? There is more.
Authenticated channel.
Yes, the authenticated channel. There's two more.
We're not taking notes.
Yeah, okay. Then wait, let me write down. So the dimension one, I will write it already a bit on the stronger way. So Nigel said dimension 2, and then he complemented it has to be a single photon source, then it's also related to dimension 2, but it has to be the 0, 1 and the plus minus state. If it's some other state, I mean, the analysis would be different if they are sending Y states or some combination of them, okay? So, and it's connected to the sources and the measurement device. So, I will write them separately. So, source needs to be there. So, they deviate for states. And in here we have all these extras. So like, okay, it needs to be a single photon, or it needs to be dimension 2. And the measurement device, measurement devices, which needs to be making Z and X measurements. If it's not X and Z measurements, I'm not estimating QX and QZ. Maybe before the question, let me write the authenticated channel. So there was the authenticated channel, and because I have a comment about this, authenticated channel. So if you are from maybe classical crypto background or know something more about authenticated channel, you might have heard that you actually need a secret key to authenticate your channel. So basically I'm using a protocol that needs secret key to generate a secret key. So maybe the proper way to say that QKD is QKD is a key expansion protocol. So I need to start with some secret key to generate a longer key. But the key needed for the authenticated channel is like just a small fraction, orders of magnitude smaller than the one you can get with the protocol at the end. I saw the microphone going around, or there is no question. No, nothing more. The random number, yes, that was talked about as well. What else?
Low noise channel, quantum channel.
The quantum channel can be noise because we are estimating how noisy it is. So we check. So QZ and QX will exactly, if my channel is noise, it will create QX and QZ. So afterwards we are going to see how much we can tolerate, but in principle I'm not assuming. So it's an insecure, noisy quantum channel. This is fine. So what about the step 4 and 5? They need to use some very complicated classical computation and classical computer, which maybe is not doing what they want to do. So actually they also need to, maybe I can put trusted classical computation. Trusted classical computation.
One more assumption is that Eve cannot read out measurements of Alice Bob, so she can interact with the channels or listen to her channels, but
exactly. So not read the measurements, not see the outcome. So also not see the result of the classical computation that she's doing. So I can say that the labs are isolated. What else? But now I finished my list, but maybe we can always find assumptions on the QuTech protocol. So. Okay, so at least these ones we have. I mean, this is also quite common in just classical cryptography, so this is like nothing new and there's not much we can do about that. Well, sorry, these 4. Quantum mechanics as well, sorry. But okay, maybe let me do it all the way around.
Glaucia?
Yes.
Sorry. Do you also need some computational hardness assumptions for hashing and the post-processing?
No. Okay. No, that's right. So if I want to have an efficient protocol, then potentially yes. Okay, let me think about it. In principle, no. So I can always use like error correcting codes, and I will account for all the leakage. So no, there is no hardness assumption. At least for the error correction, there is no hardness assumption. The things I will talk about here will be really the optimal case, which is extremely inefficient, but you can just use more efficient error correcting protocols to the cost of leaking more things to Eve, but we account for that. For private simplification, we need some specific 2 universal hashing functions, and then potentially we will approximate that to make it more efficient. But in principle, no, I don't need any computation.
But if I took rate hashing functions, that wouldn't be a problem for you?
No, but it's not it's not a single hash. You are going to use you are going to have to sample, so that's the problem. So maybe if you use a not perfect sampling, then you are in a problem, but it's not a fixed hashing, no. So in principle, we can do it, and even try to do it more efficiently without any computational assumptions. Okay. Yeah, so I wanted to say authenticated channel, quantum mechanics, we are happy about that, I suppose, but these last 4 here are quite standard in just every classical crypto, like even I say that nowadays if your lab is leaking your private key, there's nothing you can do about that. Yes.
Do you also have to assume that there's nothing beyond quantum mechanics? Maybe with something beyond quantum mechanics, you could, I don't know, do something?
I would say in principle yes. So the way we are modeling the eavesdrop, so all the results I'm going to talk about, I'm giving Eve the power of being correlated with the system in a quantum mechanical way. But so there is few results that really look into device-independent QKD in the sense of really allowing for PR box, and I think they are not able to do private simplification. Yes, it can get quite bad, but there is not many results in this direction. So at least to be on the safe side, I will model Eve explicitly in a quantum mechanical way. Otherwise, the approach has to be completely different, and none of these results hold. So I wanted maybe to say that there is the possibility of relaxing these two assumptions. So about the trust in the preparation device and in the measurement device, and I divide them separately because there is approach both to deal with the first one or the second one, and they are quite experimentally also like very different, and there is approach to deal with both of them at the same time. So I will actually already address this one now, about the source, and the other one I might just mention, I will try to mention a little bit on how to relax this on the last lecture, but I will really not go into details on the protocol of relaxing the measurement device here. Okay, so here so now I will finally tell you what is this prepare and measure that I call the protocol. The time is really flying. We start 5 days late. How much time do I have?
The chair didn't saw what was the time you started.
We started 15 minutes late.
Okay,
so you have 20 minutes.
Yeah. Okay. So I would like to talk about an entanglement-based version. So far I said Alice prepared a single qubit state, but now I would like to show you that actually we could do everything using entanglement. Not that that's a good thing, because the experimentalists wouldn't like that, but it will be also very important for the security proof. So let's say that Alice here, she prepares a maximally entangled state, which is just just one of the maximally entangled states, and this state can also be written in the X basis as. So if you are not aware of that, then it's an exercise to write the state in this base. But if I write it in the Z basis, I have perfect correlation, but also in the X basis, if I just change the basis, I still have perfect correlation. Okay, so what Alice is going to do now, she, instead of preparing the state, she's going to measure. So she measures Z, for example, first. So what happens here? If she gets the outcome 0, the states here will get disentangled, but Bob also gets the outcome 0. And if she gets 1, Bob also gets 1. And similarly, I could say, okay, she measures now X, and again, the qubits would get disentangled, but they always have the same state. So basically, this is a way of a different way where Alice is again preparing the same BB84 states. So now she sends it to Bob, this other half, and basically we have an equivalent version where now Alice prepared the state. What we could do differently, instead of Alice measuring first, she could send the qubit to Bob. So now they have this entangled state, and only then she measures her side. Okay, so this is equivalent to the prepare and measure. And now maybe the name becomes more clear because Alice prepares the state and Bob measures, while now I'm talking about an entanglement-based version, so I have entanglement. And in fact, I could, all of the things I'm commuting, I could say that actually there is a source here in the middle who prepares the state and sends it to Alice and Bob. So the source doesn't necessarily have to be in the lab of Alice, but it could be a complete a source that I don't know. And in particular, I could have my, I don't know how to draw my eavesdropper here, who is actually preparing this state, okay? So in this entanglement-based version, we are actually relaxing this, the need for the source to really prepare the states. And now the only device that I need to trust is the measurement device. And then you can note that this is equivalent to the prepare measure protocol only if Alice is really preparing single qubit states. So in the entanglement-based version, I don't really care about what she's preparing. If it's a higher dimensional system, in the end the devices are measuring qubits. So it will take care of getting rid of all possible other correlations. But if I'm talking about the prepare measure one, then I really need to have single photons. So in the entanglement-based version, we relaxed one of the assumptions. And the good thing is that actually this ends, maybe what I try to depict here with this eavesdropper is that actually I have a stronger security statement. So this fact that I actually relaxed the assumption about what state the source is preparing. So Eve can control the source. But so why is this? I mean, first I explained something where I don't need entanglement. Now I explain something where I need entanglement. So practically this is worse, but actually this is a very important description of the protocol for our security proof. So this entanglement-based version is crucial for the security proof. And this will be clear in the next lectures. For now, I will just make this a strong statement. Okay, then now maybe on my last 15 minutes. First I want to know if there are some questions about the VIII, otherwise I will move to some tools that are going to be important for describing the security proofs, like which quantities we are going to be talking about. But yeah, so first, if there are any questions. No? Good.
Why is it the case that you can derive the security proof with entanglement-based like protocol, but then in the experiment that is somehow preparing measure?
So the reason that I can do the entanglement-based version protocol, it will be clear because I have a very clear way to model the eavesdropper. So basically in this parameter estimation, I'm estimating what is the entangled state that Alice and Bob share, and what if, the way we are going to model if is to give if the purification, so the extension of this state. And this is the most general quantum mechanical description of the system that Eve could have. Because any other extension of this system, any other correlation that she could have, she can obtain by making operations in this purification. If I would try to do that for the prepare measure, it's a single state, so I can just purify it and she's completely correlated. So I cannot use this approach clearly. So the prepare measure is only going to be secure because of this equivalence that we discussed here. And this equivalence is only valid if Alice is preparing exactly the VIII protocols, or the VIII states, and not a higher dimensional system, not two photons, 3 photons. This completely destroys this equivalence with the entanglement-based version.
So in general, if you have like a place for experiment on preparing measure, then like the entanglement basically the 84 is actually more general.
Yes, it's more general, yeah. Okay, so yes, then maybe now I call it, wait, I'm losing my page. Yes. I call it tools. I will just give some definitions. The first thing I would like to define is what is a secure state. So secure here stands for classical quantum states, and these are just basically states of the following form. So why is it classical? Because basically the system of Alice, it's diagonal in some particular base. So here the base is A here. Okay? But on the other hand, the system E is a completely arbitrary quantum state. I mean, I could also have A, B, E. So here is a CCQ state, so Alice and Bob are classical, and Eve here is an arbitrary quantum state that depends on the bits of A and B. So why I'm talking about this state? Because a state of this form is exactly what we have at the end of step 1. So Alice and Bob start with an arbitrary quantum state, and they apply measurements. And when you apply measurement, you are basically measuring a specific basis, and you are getting outcome A with some probability A. So the way I will describe what is the state shared by Alice, Bob, and whatever Eve has about them is exactly this type of CCQ states. Okay, so they will reappear afterwards, so I just wanted to mention that here. And now some other very important concepts that are going to appear tons of times. This is the concept of entropy, and in cryptography you encounter all types of entropies that were already defined with different applications, but so here I briefly just want to maybe go from the classical entropy to the Shannon entropy that you might be super familiar with, but if not, just so that we are all on the same page. So if I have a variable x, that assumes value small x with probability px, then we say that the entropy of my random variable x is given by the sum over px log of px. And here we are always going to use the logarithm in base 2. Just because, well, we are going to be interested in bits, so usually our random variables will have values with 0 or 1. So we use the logarithm in base 2. And basically this entropy somehow, I mean, I think entropy is quite a vague concept, but here is the uncertainty that I have about my variable. So, for example, if my probability distribution is such that probability of 0 is 1 and probability of 1 is 0, then the entropy of x is basically, I have no entropy. On the other hand, if they are completely mixed, so I have no idea if I have 0 or 1, so both have probability 1/2, then the entropy of x is going to be maximum. So like I have one bit of uncertainty about my variable. And here, all the examples, again, they can serve as homeworks. You can just use the expression on the top and convince yourself that But these homeworks are too easy, so they don't have cachaça included. Sorry, no. Just for you to convince yourself, and the answer is already here. But we can also talk about the conditional entropy. So I want to know what is the entropy of the variable x when I know the value of some other variable y. So basically, what is the leftover uncertainty that I have the variable x when I actually have complete knowledge about the variable y. And this is defined like this: probability of x given y. So basically here is the remaining uncertainty. When we know y. And then just to give an example again so that you understand this remaining uncertainty, let's look at the following probability distribution. I hope my handwriting is not getting too horrible because I'm trying to rush a bit just to finish these concepts. So basically here I have a variable x that can assume value 0, 1, 2, or 3, and the variable y can only assume value 0 and 1. Okay? So if I know that y is equal to 0, I actually don't know if x is equal to 0 or 1, but I'm sure x is not equal to 2, because that doesn't happen with n probability. So again, it stays as a next exercise without cachaça for you to check, but the conditional entropy of x given y is actually 1 bit. So I still have uncertainty, like I have 1 bit of uncertainty, even when I know the value of y. I don't know if x is either 0 or 1, or if x is 2 or 3. But on the other hand, if I want to look at the entropy of y, given that I know the value of x, what would be this entropy? Let's see if you can already. So it's the remaining uncertainty. So what is the uncertainty? So if I know that x is equal to 0, what is the possible value of y? 0, right? So I have no uncertainty about y. So basically this entropy here has to be 0. And you can check that by using the expression above. So, I mean, this is great, classical, but actually we are working with quantum systems, so of course classical entropies are not going to be enough. So we need the generalization of such entropies for the quantum system. So I still have 5, right? So that's the last thing I will talk about today. So the von Neumann entropy of system X in a quantum state rho. So throughout the course, sometimes I will highlight which state I'm calculating the entropy from. If it's not highlighted, it should be obvious. If it's not obvious, you remind me that I forgot to write about that. Yeah, so it's always the entropy of the variable calculated in a very specific state. So in this case, the state rho. So this is minus trace of log rho. So now it's I have an operator expression. So it adds 1 level of difficulty here, but actually this can be again reduced to the von Neumann entropy if we know what is the eigenvalue decomposition of my state rho. So if my state rho can be written as sum over I, lambda I, psi I. So this is eigenvalue. value the composition, I don't know how come. Okay, so if I write my state in the diagonal basis, I know that these lambda i's here, they have to sum to 1, they are all positive, so they are basically like probabilities. So I can recover my original Shannon entropy definition, so I say that this is sum over I, probabilities that I have I log of the probability I. Oops, not probability, here is lambda. So, okay, like really recovering this expression that we have here. And okay, but now it's quantum states, or it's a bit more complicated to talk what uncertainty means here. And we can also define the conditional von Neumann entropy. So now I have a bipartite state, maybe I can say of rho AB. So I have the entropy of calculated on rho. This is going to be, I will define exactly on the same way that it was defined for the Shannon entropy, except that now we are talking about the von Neumann entropies. So the global entropy minus the entropy of B. So each of these you can calculate it independently. Here this rho is going to be just the state of both. So this is the trace of A of rho AB. And each of them you can just find the singular value decomposition and you can calculate the entropies. So I mean the thing is like, okay, now what does this entropy represent? So just to make some examples, if my rho AB is actually the bell pad, the maximally entangled state. So again, I will say the result here, but please check at home and convince yourself that you know how to calculate. So then something very weird happens, that my conditional entropy here is equal to -1, so it's like negative, so we don't really have this meaning that it's the uncertainty that we have about it, but something very interesting is that negative means if and only if rho AB is entangled. No, if and only if, no, sorry. Implies that rho AB is entangled. Not necessarily. So if I have a negative conditional entropy, I can be sure that my state is entangled. So separable states do not lead to negative entropies. But if I have a state, for example, of the form, 2 minutes, I'm finishing. Okay, let's look at this state here. So almost classical, so maybe it doesn't look classical at first because I'm using 2 different bases, but this is basically a classical state. Okay. So for this case, we actually, if you calculate, you're going to see that actually the entropy is 0. Because basically in this case, whenever I know the state of Eve knows completely what is the state of Alice. And if you notice, that is also, actually this is almost a CC state, so completely classical, but I can also see it as a CQ state. So here I have Alice, and here is my rho E given 0, and here is my rho E given 1. So this is a sticky state, this type of state that we started discussing. Final comment, for CQ states, entropy of A given B is always positive. So for this type of states that are the ones that we are going to be interested in, we can recover this interpretation that these conditional entropies how much uncertainty I have about the classical system A once I have the quantum information of the system B. Okay. Okay, so I will stop here for today, and then tomorrow we will use all these entropy security codes. If there are no more questions.
So, very quick question, if you have any.
Thank you for the nice presentation. I'm not sure whether it's a quick question. If not, maybe we can after the coffee break. You said in the beginning that the security proof for BB84 was done in 2015 or something? 5. 5, okay. Yeah, but still it's 25 years later. And if you present me the protocol, for me it's somehow from my naive point of view, it makes sense that it's secure. Can you sketch a bit what is so difficult in proving security?
So maybe the most difficult point here is that I want to estimate how much information Eve has so that I can shrink this information, but Eve doesn't have classical information. She has quantum information which could be completely arbitrary, like from all the rounds of the protocol. And theorems for what happens with a classical string once I shrink it to a smaller string in the presence of quantum information, they came much later. So this would be, let's say, one reason. The other reason is people had to have the insight to go for the entanglement. Another possible proof that I mentioned before is to go for this. First, I distill my state, or at least I make an equivalent protocol where I'm distilling. But now it's obvious for us after we see the equivalence of entanglement based, but the BB84 protocol, they didn't even present it in entanglement based equivalent version. So I think these things sort of took steps. But mostly it's the difficulty in treating side information that is quantum, which is difficult until today in many scenarios.
Thank you.
More questions you can ask Glaucia later. Thank you very much, Glaucia.